Angelina.
In our elevator experiment, we start off with an elevator. Alright, no, wait, no, I need to draw this. Okay, so we begin with an elevator, and inside we have the person who is on the scale. Now, the forces acting on this will be first the force of gravity. And also the force normal provided by the elevator. Now initially these two forces will be balanced since the person is at rest, so since it's not accelerating, the forces must be balanced. Then, as the elevator begins to accelerate, we still have the same force of gravity. However, in this case, since the elevator is accelerating upwards, the forces are not balanced, and the force normal is greater than the force of gravity. Then, as the elevator reaches a constant velocity, when it's done accelerating, the forces are once again balanced, since it's not accelerating. And then finally, when the elevator comes to a halt, we have the same force of gravity. However, this time the force of gravity is larger than the force normal, since the elevator must come to a stop and then decelerate in the downwards direction. So then you can see that there are varying force normals throughout the elevator process. Initially, we have the force normal equal to the force of gravity, which would, and since force normal is equal to weight, we would read the person's normal weight. Then as the elevator accelerates, the force normal must be greater than the initial one in order for it to accelerate, since you need a net force for the elevator to accelerate. Then in the third one, since this is a constant velocity and the forces are again balanced, the force normal will read the normal weight. And then finally, and the last one, when you're decelerating at the top, you have the force normal will be smaller than the other ones, so you'll read a lower weight.
So when it's not accelerating, Langston's weight is 162 pounds, and also goes to 142 pounds, and the maximum of 180 pounds. Converting that to kilograms is 73.6 kg, 64.54 kg, and 81.81 kg, and multiplying by 9.8 to get the normal force in newtons is 721.28, 632.492, and 801.738 newtons. You can cut. So when the acceleration is positive, then you can figure out the net force by subtracting these numbers to get the net force of 88.8 newtons. And by saying net force equals mass times acceleration, 88.8 equals 73.6 A, causing A to be 1.2 meters per second squared. And then the other normal force, 721.28 minus 801.738 equals negative 80.46 newtons. And using the same formula, 80.46 equals 73.6 times acceleration, and acceleration is negative 1.09 meters per second squared. Okay.
Okay, so to find the velocity, we have the velocity equals the distance over time, and roughly each story should be 3.3 meters. and it'll take around 1.5 seconds to travel that distance. So during the distance between the acceleration and deceleration, when the velocity is constant, it should be at around 2.2 meters per second. And then we say that the velocity final is equal to the initial velocity plus acceleration times time. But the velocity initial will be 0. So then we have the velocity final equals the acceleration times time. And so the time will be equal to the velocity divided by acceleration. We calculated before that the acceleration is equal to 1.2 meters per second squared, and the velocity is 2.2 meters per second, like we just did that. And then the time should therefore be 1.83 seconds for acceleration.
I'm friends with the monster that's under my bed. Get along with the